spacecraft that hit an asteroid. Basically, it was the very first demonstration of a kinetic impactor that would be able to protect the Earth in the case of an asteroid that is by chance coming towards the Earth and may hit it. A kinetic impactor could theoretically nudge the asteroid off to the side and miss the Earth instead of hitting it. One thing I thought I ran across since I gave my presentation last month was this thing that I found in Air and Space magazine. I don't know if I can read this here. Unfortunately, on what I see here, I have some small images of the attendees over on the right-hand side. That's sort of obscuring some of what I have on this particular chart. But what it basically says is that back on March the 23rd, 1989, an asteroid twice the size of a football field careened past the Earth at so many miles per hour. And it came within about 425,000 miles of the Earth. And if it had actually hit the Earth, it would have done a lot of damage. It would have had the energy of the equivalent of 20,000 hydrogen bombs. And if you can imagine the destruction of one hydrogen bomb and multiply that by 20,000, you can get an idea of how lucky we were by not getting hit by this incoming asteroid. If I read this correctly, anything within a 40-mile radius would have been obliterated. And if it had hit in the ocean, it could have killed millions of people just from the tsunami that it would have created. So that's something to think about when you're talking about saving the Earth from an asteroid hit. And if you think 425,000 miles away is not a near miss, look at this chart right here. Since 1914, we have had 10 asteroids that are known anyway, that have come within the distance of the moon from us. And they're listed here in the top 10 in order of missed distance. The asteroid I talked about here in the previous chart is shown down on the bottom here, March 22nd, 1989. Turns out that has a particular name. It's, I think it's, what was it, asteroid mist day or something like that. But it's really something to think about. You look at the sizes of these objects, these asteroids. There's one here at 730 meters, and that is not a small object. When you compare it to an object that could obliterate cities or countries, so it's a mean thing, and it's, you know, I think it's nice that we have the technology today now to actually have the capability of protecting us from things of this type. I threw this in here. It sort of shows you the setup of the DART mission. It turns out that the two asteroids that are in this system are called Didymus and Dimorphos. Didymus is the larger one. Dimorphos is the one that is in orbit around it. If you notice here, north of the ecliptic is up, south of the ecliptic is down. And it turns out that if you look at it in this perspective here, Dimorphos is in a retrograde orbit around Didymus, which is kind of neat. But anyway, what happened here is the DART spacecraft was deliberately impacted onto Dimorphos here, and it was on the side that was leading in it, in its way around the, in its orbit around Didymus here. So basically what you're doing is you're impacting this asteroid. So you give it a delta V, a delta velocity in the direction just opposite of its orbital velocity. So one thing I pointed out last time was the fact that most people, not knowing that there's an ejection of ejecta from the asteroid when it's hit, would write an equation for the conservancy of momentum without that one term that I show it highlighted in yellow at the top of this chart here. That highlighted term is the ejecta momentum. And that's a very important term when you're dealing with impacts on asteroids, because that term actually enhances the delta V that's imparted to the asteroid after it's hit. So the reason I put this in here is that when you read the technical papers about impacts on asteroids, you'll always run across a term that's called beta. And beta is what's called a momentum multiplication factor or momentum enhancement factor. What it is it's a change in momentum. Whoops, how do I get back up there? Here we go. It's a change in momentum divided by the momentum of the spacecraft that or impactor that hits the asteroid. So one way of, well, basically what it is it's a ratio of the total momentum required by the target from the impactor and the ejecta to the momentum of the spacecraft. It measures how effective the impact was in producing momentum from the ejecta to enhance the momentum imparted to the target. And one equation that you see quite often is that it's equal to 1 plus the momentum of the ejecta divided by the momentum of the spacecraft. So if you see a beta equal to, let's say 3, then what that means is that the ejecta produced twice the momentum as the spacecraft did, imparting to the asteroid. So it's a very important parameter, and it's a tough one to come up with. What they do is they do math modeling of ejections after, with impactors. They also do I shouldn't say full-scale tests, but they actually do impact tests also to come up with the estimate of beta, depending on the different materials that they think asteroids are made of. So here in a nutshell is what I think, in my opinion, tells the whole story of asteroid impacts. At the top, I have the conservation of momentum. Momentum of the spacecraft is equal to the mass of the asteroid plus the mass of the ejecta and the mass of the spacecraft times delta V plus the momentum of the ejecta. So what's important here is that the ejecta, when it's ejected out, after the spacecraft or the impactor hits the asteroid, the ejecta come out in one direction. However, there's an equal and opposite reaction that actually pushes the the asteroid in the opposite direction. So even though you say, if you look at this equation up here for the conservation of momentum, you can say, you'll say, hey, look, I can't get any more momentum imparted to this asteroid than what I had to begin with the spacecraft, but that's not quite right. You got to look at this as a vector equation here, so that if you have an ejecta going in the direction to the left, you have a reaction of the ejecta pushing on the asteroid to the right. So what that means is, if you have more and more ejecta with more and more momentum to the left, what that essentially does is it pushes out this momentum of the asteroid to the right even more. So ejecta actually help. You can look at this as basically a rocket engine that is formed by the impact of the impactor. The ejecta is basically similar to the exhaust particles that are coming out of a rocket engine. So the exhaust goes in one direction, but the thrust is the reaction, and that goes in the opposite direction. So the more particles that you have with more and more momentum from the ejecta, the more and more delta V you're going to get on the asteroid. So it's sort of like getting something for nothing. Of course, in this case, it's at the expense of the asteroid, but that's exactly what you want. And it's kind of a neat thing. Instead of just getting a momentum from the spacecraft, you have the ejecta that's actually helping you. I have some statistics I've thrown in here too this time. There's 4 different types of near-Earth asteroids. There's 4 different classes. They're classified by their orbits. The first one is Terra or apohele. These are orbits that are completely inside the Earth's orbit. The Aten asteroids are the ones that have a semi-major axis less than 1 AU in orbit, but the orbit crosses the Earth's orbit. Then there's the Apollo near-Earth asteroids, where they have the semi-major axis greater than 1 AU and the orbit crosses the Earth's orbit. Then there's the Amor class, and those are the ones where the perihelion is greater than the Earth's aphelion. And it turns out that Dimorphos and Didymus fall within this last category, the Amors. Now, there's another term that's called near-Earth objects. So the near-Earth asteroids are part of that. But there's, in addition to the NEAs, the near-Earth asteroids, there's also the near-Earth comets. And there's 117 of those. But it turns out that if you look at the current tally of all the near-Earth objects, we have over 30,000 of them that are known today. Of course, there's a whole lot more to be discovered, and that's kind of an unknown quantity right now. But one of the things I thought I'd point out here is, of those 30,000, there's about 2,300 of them that are potentially hazardous asteroids. And these are the ones that intersect the Earth's orbit and have a very low luminosity. So in fact, it turns out that Didymus and Dimorphos fall within this category. Okay, and this is a little size comparison here. Dimorphos is more or less this type of, this size of object that's shown over here next to, well, between the Statue of Liberty and the Great Pyramid of Giza, gives you an idea or feeling for how big, big an object that is. Didymus is quite a bit bigger, but here again, it's, when it comes in terms of objects in the solar system, it's not all that big, but obviously you don't want to have something like this coming at you at 6 kilometers per second. Okay, now I show this last time, but this is a picture that was taken by what they call the Lycia cube. It's a CubeSat that was basically piggybacking on the DART spacecraft up until about 15 days prior. And it took this picture at the time that Dimorphos was hit, and you can see the ejecta coming out very easily here. By the way, the energy of the impact was about 2.5 tons of TNT. And I thought I'd throw this one in here too. It gives you an idea of all the different telescopes that have been involved in this project. Most of what you see in here are telescopes that were in action at the time of the impact, getting information on, the ejecta and things of that type. All these that are shown over here are land-based, except over here in the lower left-hand corner, these are all space-based, the Hubble Space Telescope, James Webb, and Lucy. And if you look over here, this is a picture that was taken by Hubble. And what's kind of interesting about this one is that you can see that there's not just one tail. If you kind of look at it very carefully, but there's an indication that there are two tails here that have been formed, which is kind of interesting. This is not something that was expected. And there was a question last time as to what happened, what happens to the ejecta. And, my answer last time was basically it's going to dissipate. Well, it does dissipate, but it's kind of interesting to see how it dissipates. Apparently the ejecta was thrown out in a direction that was sort of like leading the asteroids in orbit. So you got ejecta that's actually preceding the actual asteroids in their orbit here, and you also have ejecta that's following behind also. But I have these simulations arranged so that I show what happens from on 1 year delta T's. So the first one here is pretty much, I think 1 year after the impact. And then the next one down here, you can see what happens after 2 years, then 3 years, 4 years, 5 years, and 6 years. And what's kind of neat here is you can see that after 6 years, you basically have closed the loop on the ejecta there. It basically envelops the entire 360 degrees around the sun here. What's kind of neat also too is you can see that at least in this view, it looks like the ejecta overlap the Earth's orbit. Now, I don't know, obviously where it intersects doesn't necessarily mean that that's where the Earth is going to actually encounter any of the objects or the ejecta, because the ejecta may be, several 100,000 miles either above the plane of the ecliptic or below. But I thought it was kind of neat because if you look where that intersection is, Earth is right here. This is at the end of September. I would imagine that the intersection here was right around Christmas time. So wouldn't it be neat if you could go out at Christmas time and you can see some, little meteoroids or meteors coming through the Earth's atmosphere, and you can say, hey, look, we actually have some of the DART ejecta coming in at this time. Anyway, what I really wanted to get to is the results that have been coming in here. As I mentioned last time, the period of the orbit of Dimorphos around Didymus changed by 32 minutes. Actually, I think that should have been a minus. The orbital time has actually shrunk by 32 minutes. And what that means is then that the radius of the orbit has changed by about 50 meters, according to my calculations. And that's kind of interesting because prior to the impact, they thought that there probably won't be more than more than 10-minute change in the period. And here they got a 32-minute change. And in fact, if you look at what I have here, this is very interesting. Dimorphos was 8.75 million times more massive than the DART spacecraft, but its orbital period was changed by 4.5%. That's 26 times greater than the criterion for success. So they certainly got a great impact on the Didymus system there, without any doubt. There's going to be a spacecraft launched by the European Space Agency in 2024. Let's see. Yeah, let's see. What's the name of that? Hera. Yeah, it's a spacecraft called Hera, and it's actually going to not only take pictures of Dimorphos at that time. That'll be 2 years later in 2026. But I also have some CubeSats along with it, and one of which will attempt a landing on Dimorphos, which would be kind of really neat to see. But anyway, the real thing that I saw just a few days ago was some article that said that they had done some experiments, and it looked as though the best match that they had with what DART, the DART spacecraft did had a beta of 3.4. And what that means is that the momentum imparted by the ejecta was 2.4 times the momentum imparted by the spacecraft. So you can see that the ejecta played a very important role in this, in this whole case here. What I think most people are wondering about is how representative was the DART mission with Dimorphos amongst all the asteroids. Didymus and Dimorphos are only two of thousands and thousands of asteroids, and the question basically is how representative is this number? Can we rely on this or not? So that's something that they're going to have to really think about. But it turns out that the delta V that was imparted, according to my calculations, the delta V imparted to Dimorphos was 2.38 millimeters per second. And that doesn't sound like a lot, but that's a lot more than what they expected. And then I'll go over here. I thought this is kind of interesting. This is the actual light curves that were compiled from all the telescopic views on Earth that allowed the scientists to estimate the effect on the period of the orbit of Dimorphos around Didymus. And as you can see on these blow-ups here down on the bottom, On September the 29th, which was about 3 days after the impact, the light curve shows a significant dip at this time right in here, and that obviously corresponds to Dimorphos being eclipsed by Didymus. If you go over here to October the 4th, the same thing happens over here, that you get a dip over here, and it matches an orbital period of 11 hours, 23 minutes. The expected dips are shown by the brown arrows here, and they're completely off. And you can see that you know, that the 23-minute change in the, or 32-minute change in the orbit really stands out here. And I have one final chart that I thought I'd show you here. This is the bad news. What I did was I came up with some calculations to show the length of time from the asteroid impact by a kinetic impactor that's required in order for an asteroid to be diverted 1 Earth radius at the time it crosses the Earth's orbit versus delta V. And on this plot, I show the delta V that was imparted to Dimorphos by the DART spacecraft. It's over here. Reading this, you can see that if we wanted to divert Dimorphos so it would not hit the Earth, we would have had to launch the spacecraft in enough time so that it would have gotten to Dimorphos 50 years prior to the actual encounter with the Earth. And that is something to really think about, because what that means is that, number one, you have to have a very early detection of an asteroid that may be hitting the Earth. And number two, you have to have the means of precisely propagating an asteroid's orbit so that you can accurately predict that it's actually going to hit the Earth. That is not easy. So this is something that you don't see in the articles that are written about the event, but I thought it was important to show. I remember that when I was listening to the director of NASA describing this mission and saying, you know, all the kudos about how great a job it was, it certainly was a great mission. The problem is that, you know, there's a lot more to it than just one test. You need to have a lot of, I guess what you have to say, you have to advance technology to the point where instead of getting a delta V of about 1/4 of a centimeter per second, we need to get up there, in my opinion, closer to about a centimeter, a full centimeter per second, or 2 centimeters. 2 centimeters, if you get a delta V on an asteroid of 2 centimeters per second, that means that we need to launch the vehicle in time so that you get an impact on the asteroid 10 years prior to its encounter with the Earth instead of 50. But that's something to think about. And that's the end of that.
Okay. Now,
thank you, Ken. That was great.
ESA is doing a follow-up mission for that, right?
Yeah, Hera.
Hera.
Yeah, that'll be launched. As I understand it, it's scheduled for late 2024, and it's scheduled to be arriving at Dimorphos and Didymus sometime in 2026.
Okay.
Well, thanks again for giving us so much more information than was been covered elsewhere. It's really nice to have that perspective. Any questions for Ken?
No,